Hello everybody, I welcome you all to NCAS Geology class. Today I will discuss about some of the physical properties of minerals. Let me discuss about pseudomorphism. Pseudo means false, morphism means external form. So here a mineral assumes the shape or form of a mineral which does not belong to it. This process of assuming the shape of some other minerals is called pseudomorphism. For example, martite. Martite is actually hematite, but it takes the structure of magnetite. That's why it is called as martite is called a pseudomorph of hematite after magnetite. Martite composition is hematite, that is Fe2O3. When hematite is crystallized, it takes the system hexagonal, or it is a hexagonal form. But martite has a cubic form. Its composition is Fe2O3. It is hematite, but its form structure becomes cubic, or it is the form of magnetite. So the morphology of martite is that of magnetites, but martite is not magnetite. So martite has a false morphology. That's why it is showing pseudomorphism. So false form of magnetite. So martite is described as pseudomorph of hematite after magnetite. The pseudomorphism is produced by several causes such as incrustation, infiltration, replacement and alteration. Coating or deposition of one mineral on the crystal surface of another mineral, as we see quartz coating on fluorspars. Quartz is hexagonal, whereas fluorspar is cubic. So quartz will assume the shape of fluorspar, which is cubic form, but quartz is hexagonal. So quartz can be said to have a pseudomorph structure of fluorspar. Similarly, infiltration. When a cavity is occupied by previous mineral, when the cavity occupied by previous mineral is refilled by mineral matter of another substance, so the shape of the earlier mineral is assumed by the later mineral. Similarly, we find replacement. Here, slow gradual molecule per molecule replacement of one mineral by another mineral gives rise to the structure of replaced mineral by the replacing mineral. So, replacing mineral takes the morphology of replaced mineral. Similarly, alteration is gradual chemical change which crystals sometimes undergo, retaining the form of replaced mineral with different composition, as we find serpentine replacing olivine. So olivine alters to serpentine. So this is a type of alteration. So alteration, replacement, infiltration, incrustation, these are the methods by which a mineral assumes the false shape of a mineral, and that's why it is said that it is displaying pseudomorphism. Then polymorphism. What is polymorphism? Poly means more than one. So more than one morphology, more than one form. So when two or more minerals have the same formula but different crystal structures, they are said to display polymorphism. For example, calcium carbonate. Calcium carbonate exists as calcite and aragonite. So it is said to exist as hexagonal, which is calcite, and orthorhombic, which is aragonitic. So it shows two types of morphology. That's why it is said to be dimorphic. Calcite or calcium carbonate exists in two types of morphology, in hexagonal and orthorhombic, that is in form of calcite and aragonite. Similarly, diamond and graphite, they are made up of carbon, but graphite is hexagonal whereas diamond is cubic. So they show dimorphism. Similarly, anatase, rutile, brucite, all are having composition TiO2. So we can say it is trimorphous. Rutile is tetragonal, having specific gravity 4.2. Anatase, tetragonal, but specific gravity is 3.8. Brucite, orthorhombic, specific gravity is 4. So they, even if here the system may be same, but their density becomes different. It is due to atomic packing. The packing may be of different types, because of which density varies. So density more means more atoms in unit space. Here more atoms in case of rutile, the more atoms within a limit, within a volume, within a definite volume. So 3.8 means less atoms within the same volume. So it is related to atomic structure. So here we find trimorphous, that means in three types of morphology these minerals having composition TiO2 exist. Similarly, we have orthoclase, microcline, sanidine and aluminous silicates, which may be trimorphic. The polymers form in different pressure, temperature conditions and in different chemical environments. Hence, they act as geological thermometers. They indicate the environment, they indicate the pressure and temperature of their formation. Reversible polymorphic transformation is found in case of quartz, tridymite, cristobalite. Quartz changes to tridymite at a temperature of 870 degrees centigrade and changes to cristobalite at a temperature of 1470 degrees centigrade. Quartz is alpha quartz when it is at a temperature less than 573 centigrade. It becomes beta quartz after 573 degrees centigrade, and beta quartz may change into tridymite at a temperature 870 degrees centigrade and into cristobalite at temperature 1470 centigrade. So these are the different forms of silica. So we can say silica is displaying polymorphism at different temperatures, different pressures, as a result of which we see that the morphology changes. Below 573 centigrade it is alpha quartz. Above 573 it is beta quartz. All can be called as beta quartz, but it may be, beta quartz may be converted to tridymite, it may be converted to cristobalite. If temperature is more than 1730 degrees centigrade, the silica is no more existing in form of a mineral, it becomes a melt, silica melt, we get silica melt. So these are reversible polymorphic reactions. We have irreversible polymorphic reactions such as marcasite to pyrite at 450 centigrade. Marcasite changes to pyrite. It is a monotropic transformation or transformation in one way, marcasite to pyrite, not the reverse. Pyrite is cubic, high temperature fall. Similarly, conversion of diamond to graphite is monotropic transformation. Graphite is stable, diamond is metastable, and hence gets converted into graphite at high temperature and pressure conditions. Similarly, we have isomorphism. In case of isomorphism, the crystal structure remaining same, composition varies, as we find in case of olivines, plagioclases, they display the phenomenon of isomorphism. Olivines, they are orthorhombic in crystallization. Plagioclase, they are triclinic in their crystallization. But olivines, we have a varieties of olivines from magnesium variety to iron variety. Similarly, plagioclases, they are having varieties from sodium variety to calcium variety. Composition is variant, but structure is same. The crystallization system is same, isomorphism. Similarly, paramorphism, it is a phenomenon in which a crystal whose internal structure has changed to that of a polymorphous form without any change in external form. So here internal structure is changed. It results due to change in molecular concentration. Rutile changes to bruchite, aragonite changes to calcite. Internally they get changed, but external form is same. Calcite is hexagonal, but aragonite is orthorhombic. So form will be hexagonal, but internal structure will be orthorhombic, aragonitic. So this is a case when you talk about paramorphism. Internal structure changes with same morphology. Then we will discuss hardness. It is the resistance of the mineral to scratching or to abrasion, abrasive forces. So it is denoted by H. Hardness is denoted by H. Hardness. Hardness is defined as the scratchability of a mineral. How easily it can be scratched or how it resists to scratching. Hardness is measured by sclerometer. The evaluation of hardness is made through assessment of reaction of the crystal structure to stress without rupture. Stress is applied on its surface, scratching is being done, and how easily the mineral surface is being scratched, that shows its hardness or resistance to scratching. Minerals possessing metallic bond yield to scratching through a groove, and those possessing covalent ionic bond, they behave as brittle minerals, and thus they yield through microfracturing or rupture in very fine scale when they are subjected to scratching. The hardness of mineral increases through increasing ionic charge or valency, decreasing ionic size, increasing density of packing of atoms, increase in bond strength, increase in concentration of bonds. So, more the number of bonds, harder is the mineral. Diamond possesses closely spaced, very strong bonds, for which it is the hardest mineral. Diamond is said to be the hardest mineral. Talc, for example, it has basal silicate layers and are held together by weak van der Waals force or hydrogen bonds, because of which it is very soft. Because it has soft bonds, hydrogen bonds, with small number of bonds, it becomes very soft, and that's why talc is softest, whereas diamond is the hardest. The Australian mineralogist F. Moho in 1824 developed the scale of hardness consisting of 10 minerals with hardness value from 1 to 10 based upon the scratchability of minerals. That is, which mineral scratches to which mineral or abrades to which mineral. The mineral that is abraded is softer than the mineral which abrades it. So that has been discussed here. So this is the table. We have the Mohs scale of hardness represented by talc hardness 1, gypsum 2, calcite 3, chloride 4, apatite 5, orthoclase 6, quartz 7, topaz 8, corundum 9, diamond 10. Diamond is the hardest substance. And this is a relative hardness scale. It is not a absolute hardness scale. If it would have been absolute scale, then diamond would have been exactly 10 times harder than talc. But that is not the case. If we take into another hardness scale, which is generally absolute hardness scale, noob hardness scale, talc is having hardness 1, gypsum 32, calcite 135, chloride 163, apatite 430, orthoclase 560, quartz 820, topaz 1340, corundum 1800, whereas diamond is 7000. So this shows that the hardness of diamond is very high. It is well explained by this graph. If we take in the relative hardness on this diagram and absolute hardness in this scale, in this direction, we have talc soft 1 hardness, gypsum 2 hardness, calcite 3, chloride 4, apatite 5, orthoclase 6, quartz 7. But if you take into absolute hardness is increasing. When you talk about diamond, whose Mohs scale hardness is 10, but it is several times harder than talc. It is about 7000 times harder than talc. So when you talk about this absolute hardness scale and relative hardness scale as shown here, and we see that corundum, this is corundum having Mohs scale 9, but absolute hardness is about 400. It is 400. So corundum is twice harder than topaz, because topaz is having hardness 200. So corundum is twice harder than this is topaz. 4 times harder than quartz, because quartz is having hardness 100. Corundum is having hardness 400. That's why it is 4 times. 8 times harder than orthoclase. Orthoclase is having hardness 50. So it is 8 times harder than orthoclase. So this is a absolute scale. So hardness is a vectorial property that are determined by scratching one mineral over the other and vice versa. The materials which are of help in identifying the hardness are fingernail. Generally, minerals having hardness less than 2 can be scratched by nail. Copper coin, it is generally having hardness. Through it, we can know the hardness of mineral up to 3. Steel pocket knife, it can indicate the hardness of mineral up to 5. Window glass, it is having hardness equal to 5.5. Steel of a file, hardness 6.5. And stick plate is having hardness 7. So generally, in order to know the hardness of the mineral, we rub the mineral on the stick plate. If stick plate is being rubbed, then the mineral is harder and it is having hardness more than 7. Otherwise, it is having hardness less than 7. The crystals of the minerals may be show variable hardness in different directions, as you find in case of kyanite, which is otherwise called disc thin, which is having double hardness, 5 along the length and 7 across the length. Calcite is having 2 on the basal pinnacle and 3 on other surfaces. So the hardness of mineral is linked to chemical composition. Hydrous minerals are having hardness less than 5. Halides, carbonates, sulfates, phosphates, they have hardness less than 5.5. Mostly sulfides, they are having hardness less than 5. And most anhydrous minerals are having hardness more than 5.5. As you see, quartz, topaz, corundum, they are having hardness more than 5. So this is all about hardness. Now let us discuss what is tenacity. It is defined as the manner in which minerals respond to short-term stresses at normal surface temperature and pressure conditions. How the minerals respond to stresses. Accordingly, minerals are classified as sectile, malleable, flexible, elastic, and brittle. So, whether the minerals can be stretched easily, whether they are flexible, whether they are elastic, whether they can be flattened. So, on that basis, the terms are being used. Sectility, mineral can be cut with a knife, such as graphite, steatite, gypsum, they can be easily cut by knife. So they are sectile. Malleable, they can be flattened into plates. A mineral is malleable if slices cut can be flattened under the hammering. Native gold, copper, silver, they are found to be converted into sheets by application of pressure. So that's why they are malleable. Ductile, when the minerals can be stretched into thin wires, they are said to be ductile. Here native metals can be drawn into thin wires. We can find the copper minerals, copper, silver, they can be stretched into wires, so they are ductile. Flexibility or flexible, it is the bending property of the mineral. Here the mineral plates or laminae remain bent after the pressure causing the bending is removed. So here they are said to be flexible, they can be bent under the application of stress. Elasticity or elastic, here so flexibility is shown by talc, selenite, chloride, they can be bent. In case of elasticity, the mineral bent under stresses can return to the original shape when the stress is removed or stress is released. As we see in case of mica, mica can be brought back to its original position after the stress is released. Similarly, brittleness, the minerals, they are breakable. They respond to stress elastically initially, but they may yield to fracturing after a little or little more stress. When the elastic limit is being crossed, the materials break. They are said to be brittle. Minerals which respond to stress elastically may yield to fracturing after little or no plastic strain. They are brittle. So materials may behave elastically to certain extent. When the stress will be more than the elastic limit, it will be ruptured. It may break. Such as iron pyrites, apatite, feldspar, they are generally brittle. Friable, the minerals which can be crumbled easily into powder form, friable. Pulverulent property, the minerals which are powdery and have little or no cohesion, as we see in case of clay, chalk, they are pulverulent property they have. When it is friable, they can be crumbled into powder form easily friable. Generally, minerals with metallic bonding are malleable, ductile. That with ionic bonding are brittle, and that with hydrogen and van der Waals bonding, they are flexible, cleavable. So this is all about the properties under tenacity. Then let us discuss what is fracture. The minerals which do not exhibit cleavage, they may break with an irregular surface. The nature of this broken surface is called as the fracture. So when the mineral breaks in a direction other than that of the cleavage direction, produces fracture. It is related to atomic structure such that the bond strength is found to be uniform in all directions. That's why it breaks with irregular surface. The fractures are described as with several terms such as conchoidal, where the fracture surface is curved, concentric, concave or convex, like a shell. Here the bond strength is found to be uniform in all directions, as we find in quartz, glass, chalcedony, garnet, obsidian, opal. These are mostly glassy substances. Or silica dominated substances. Then uneven, if it is found that the broken surface is showing fine-grained minerals, where mineral aggregates are oriented randomly, there the surface is not totally concentric curved, but it is showing fine-grained minerals showing ups and downs. There it is said to be uneven. The random aggregates are oriented randomly. They present up and down surface, rough surface, gypsum, granular, olivine, even. Here the fracture surface is nearly or almost flat, as you see in case of flint, chart, even. Splintery, when the minerals present fibrous aggregate break or separate into fibers, they produce splintery fracture. So, fibrous aggregate, minerals break into fibrous aggregate, there we say that fracture is splintery, as we find in case of selenite, a variety of gypsum, serpentine, amphiboles. The fibrous amphiboles are called as asbestiform minerals because of the strength of the fibers, because of the very property of the fibers. They are said to be asbestiform minerals. So the property of breaking of minerals into fibers is called the splintery character or splintery fracture. Hackley, here the malleable metals break along ragged or jagged or sharp edges, which are described as Hackley fracture. That means the surface is filled with very sharp, pointed, needle-like surface. This is Hackley fracture, as we find in case of native metals. So, splintery fibers, Hackley, sharp, pointed minerals. The mineral surface presents sharp points, needle-like points. Hackley. So this is all about fracture. Then let us discuss what is cleavage and parting. So cleavage is the property of the mineral by virtue of which it breaks along plane smooth surfaces, and it is due to its very atomic structure. Property of mineral by virtue of mineral breaks along plane smooth surfaces. It is related to atomic structure and related to bonding present. There are structural defects in those planes along which the mineral breaks easily, producing plane smooth surfaces. And these minerals which yield to stress along plane surfaces or along the planes of defect, they produce planar surfaces, and the planar surfaces are called as cleavage surfaces. Why the mineral shows cleavage? It possesses atoms arranged in layers having strong bond along the layers and weak bond between the layers. In such case, the minerals yield to stress along layers, producing plane surfaces called cleavages. These cleavages surfaces are found to be closely and uniformly spaced. Depending on the number of directions such cleavages are found, the cleavages are described as 1 set, 2 set, 3 sets, 4 sets and 6 sets. 1 set mica, 2 sets amphiboles and pyroxenes, 3 sets calcite, 4 sets fluorite, 6 sets sphalerite. So basal cleavage, it is also called C-pinacoidal cleavage, as you find in case of mica, graphite, talc. So basal pinacoidal surfaces are the cleavage surfaces. They possess covalent bond along layers, bondrous bond between the layers. Cleavage is obscure in beryl and absent in quartz. Quartz is having uniform strength in all directions. That's why it is not present in cleavage surface. A-pinacoidal cleavage. Cleavage is parallel to A-pinacoid, as you find in case of kyanite. B-pinacoidal cleavage. Cleavage is parallel to B-pinacoid, as you find in case of gypsum and feldspars. Prismatic cleavage, they are found to be parallel to prisms, as you find in case of pyroxenes and amphiboles. Because amphiboles and pyroxenes, they possess prismatic form. Cubic, here the cleavages are tridirectional. There are triangles. So they possess 3 sets of cleavage, as you find in case of galena. The very form of galena is cube. Octahedral, here the cleavages are found to be parallel to the faces of an octahedron. So in octahedron there are 8 faces. So along 2 opposite faces, 1 set of cleavage. So there will be 4 sets, as you find in case of diamond, fluorite. Dodecahedral cleavage, 6 types, 6 sets. It is parallel to the faces of dodecahedron. In dodecahedron there are 12 faces. So against 2 opposite faces there is 1 set. Thus there are 6 sets, as you find in case of sphalerite, 6 sets. Rhomboidal, here the cleavages are parallel to the faces of the rhomboedron, as in case of calcite, 3 sets of cleavage. Depending upon the ease at which the crystal cleaves and the perfection of the surface obtained, the cleavage is said to be perfect, good, poor or indistinct. Mica, galena, calcite, fluorite, they show perfect cleavage. But parting is something different from cleavage, but here we also find formation of plane surfaces, but it is not related to atomic structure. Minerals develop plane of weakness through stress, twinning, exsolution. These planes are limited in number and are not uniformly found to be spaced within the minerals, because they owe their origin to stress, they owe their origin to twinning, exsolution. So along such planes, they break easily, producing plane smooth surfaces. These surfaces are called parting, as we find octahedral parting in magnetite, basal parting in pyroxene, rhomboidal parting in corundum, and parting in garnets. So this is all about some of the properties such as cleavage, parting, fracture, then tenacity, then polymorphism, isomorphism, and pseudomorphism. So in my next class, I will discuss about the properties of minerals based upon light. Thank you all for giving a patient hearing to my present talk.